Greetings A-level chemists, welcome to this video all about redox titrations, everyone's favourite topic. Okay, before we just get into the answer, we're going to draw a little storyboard trying to convert all of that confusing text into a nice picture because a picture paints 1,000 words. So, you've got a student and they're doing an experiment to determine the percentage of copper in an alloy. In the experiment, we have the mass of the alloy and that is dissolved in conc nitric acid, ensuring that all the copper present in the alloy is converted to copper 2 plus ions. Cool. So let's start drawing that first section. So we've got this mass of the alloy. It's dissolved in conc nitric. And what we generate is copper 2 plus. Okay, so imagine this is my solid. So I've got 984 mgs. And what I'm going to do is dissolve it in nitric acid to liberate copper 2 plus. Okay, and then what we're going to do is we're going to make it up to 250 centimeters cubed in a volumetric flask. Okay, so we've done that section as well. And then what we're going to do is we're going to take a sample of this. So we're going to take 1/10 out. So I've got copper 2 plus in here. And then I'm going to take 1/10 out and put it into a conical flask. So I'm going to have 1/10 of the number of moles here. 1/10 of the number of copper 2 plus moles. Okay, so I've done that bit, taken an aliquot out. And then what happens is potassium iodide is added. Okay, so I'm adding Ki, and I have the following reaction. So the 2 plus and the I minus react to form copper iodide and I2. So I2 is given out, okay? So in here, after that reaction, so I add excess Ki, and what happens is now, if we think about this, try and draw that conical flask bigger, I have some I2 in here from that first reaction. So the I2 is generated from that first reaction, okay? And then the iodine that is released or liberated is then titrated with sodium thiosulfate. And if I do a titration with sodium thiosulfate, that allows me to determine the number of moles of I2 that reacted. Okay, so what do we know about the sodium thiosulfate? We know the concentration. So the concentration is equal to 0.08 moles per decimeter cubed. The volume is 9 centimeters cubed. Divide that by 1,000. So it's 9 times 10 to the minus 3 decimeters cubed. Okay, using the data provided, determine the percentage by mass of copper in the alloy. Ensure that your final answer is given to an appropriate number of sig figs. Okay, so what I'm thinking here is 3 significant figures would be appropriate because that's what's quoted in the question. All right, where do we start? Do we start with number 1 or do we start with number 2? I'm going to start with equation number 2 because I know something about the sodium thiosulfate. I know the concentration and I know the volume. So if I know the concentration and the volume, I can work out the number of moles of S2O3 2 minus. So step number 1 is the amount of S2O3 2 minus. Okay, it's really worthwhile putting headings in your working out, okay? I think that will pay dividends because if you don't, the examiner doesn't really know what you're referring to, okay? And is trying to follow your working. So remember that N equals C times V. These are solution calculations. So the concentration is 0.08 and the volume is 9. So 9 over 1,000 multiplied by 0.08. And what does that give me? So that gives me 7.2 times 10 to the minus 4 mole of sodium thiosulfate. Okay, with that information, what can I do? I can use the molar ratio now to work out the number of moles of I2. So what I do is the amount of I2. And the amount of I2 here is in 25 centimeters cubed. I'm just going to put that label, okay? It's going to be helpful. In 25 centimeters cubed. In that portion. So, as 2-to-1 ratio, therefore, it's going to be 7.2 times 10 to the minus 4 all over 2. So what does that give me? So that gives me 3.6 times 10 to the minus 4 moles of I2. Okay. And then I'm going to go to equation number 1. So now I'm going to go to equation number 1. Because all of that I2 from equation number 2, or using equation number 2, came from equation number 1. So it all came from here. So it all came from here. Okay. So if all of that I2 came from here, what can I do? I can then use the molar ratio in equation number 1 to work out the number of moles of copper 2+. Okay. So then I can say the amount of copper 2+ ions in 25 centimeters cubed. And that is going to be exactly the same. Tell a lie, it's going to be that number multiplied by 2 because the molar ratio is 1 to 2 for the iodine to the copper 2+. So as 1 to 2, therefore it's going to be 3.6 times 10 to the minus 4 multiplied by 2. And that takes us back to 7.2 times 10 to the minus 4 moles. Okay, and that's the amount of copper 2+ in 25 centimeters cubed. But what I need to do is work out the amount of copper 2+. So now I've worked out the amount of copper 2+ in here. What I need to do is work out the amount of copper 2+ in that larger volume, in that 250 centimeters cubed. So what do I need to do? This time, if we took a 10th out going from left to right, I need to work out what's in the larger volume. I'm going to scale up by a factor of 10. So the amount of copper 2+ in 250 centimeters cubed. So it's going to be 7.2 times 10 to the minus 4 multiplied by the larger volume divided by the smaller volume. So it's going to be 10. So this becomes 7.2 times 10 to the minus 3 mole. Okay, so that's the amount of copper 2+ in the volumetric flask, and it's also the amount of copper 2+ in that beaker when we first dissolved the alloy. Okay, where do we go next? So now I can say, let's work out the mass of copper. So the mass of copper in the alloy, to work out the mass, it's going to be the atomic mass, or the Ar, times the number of moles of copper. So the mass is going to be equal to 7.2 times 10 to the minus 3 multiplied by 63.5. So what do we get? So we get 0.4572 grams. Okay, we're almost there. So now I need to work out the percentage by mass of copper in the alloy. So the percentage, that's the last bit. Okay. So to work out the percentage of copper in the alloy, I'm going to take the mass of copper in the alloy, which I've just worked out, divided by the total mass of the alloy. But the problem here is I'm given the mass in milligrams, so I need to convert that into grams. So I'm going to do 984 over 1,000 times 100 to get the percentage. So what do we get? So if we process that into 3 significant figures, we get 46.5 5%, and the job is done. Ta-ta.